Bacchus early on found these dendrites. The dendrites were kind of like spiky growths on the cathode. And so you see that would, he found that the heat in tritium in his experiment usually didn't occur until he saw these dendrites. And the one-dimensional aspect of in the greater area of the dendrites would tend to go with the H2 and would not be consistent with T1, okay? Also, it seemed to us that our experiments in the case at least of heavy water, always tended to follow the deposition of sufficient platinum black. And so there again would be a surface effect because the blackening is due to the fact that you've got many small particles that are scattering the light in all sorts of directions. Srinivasan and others in India have found tritium patterns that are at the surface of metals, okay? And of course at the surface you'd have neutrons on this side, so you would have a number of one-dimensional chains that could give the effect. Also, we should mention capillary fusion. Capillaries that, capillary that was made of a chemical having heavy water in it had a large voltage, okay, discharge across it and gave out bursts of neutrons. And I maintain that if they had looked hard enough, they would have found some tritium too. But apparently they're just looking for neutrons. This is back in the 1960s. A real wild idea here would be that the Z-pinches that you find in reactors where they get neutron bursts is associated with the capillary fusion. But once again, this thinning down to get a cylindrical geometry increases area, and it also increases the one-dimensional kind of dendritic effect. Okay, so let me pause there and just ask if there are any questions. That's the first talk. Do we still have time for the second talk before lunch, or do you want to?
Well, it's pretty much noon. If we take discussion now, it might be a time to break, and you can.
Yeah, give the other talks later. Yeah.
I'm curious to know how this mathematical representation explains the mechanism for overcoming the Coulomb barrier and dumping the energy into the...
Okay, that'll be explained in the phonon laser model this afternoon. But basically, just to give you a hint of this, if this is a surface effect, what we're using probably is the swimming electron layer. So we're up against this if we've got a metal. Here's the swimming electron layer. Here's the atoms, the deuterons, or what have you. And essentially, this is kind of wild, and you're going to have to bear with me a second here. But you know the zero-point field. You've heard of the zero-point field. It's well known the zero-point field decreases at a wall. Okay, are you familiar with the Casimir effect? So you see that gives evidence that the zero-point field, those modes all decrease at a wall. And so anything near that electron mirror wall could be a decreased zero-point field that would then no longer support the electron in its usual ground state. What you would have then is you'd have a collapse of the electron down to maybe 1/10 of the ordinary Bohr radius. This would give you a pseudo-neutron, if you will. This thing with the electron much closer to the proton would look like a pseudo-neutron. Electrons have been found streaming out of these samples. So Srinivasan mentioned that to me, that in their work they see almost an electron wind coming out of this. So it appears the electrons basically guide these things in. They do away with the Coulomb barrier, and then they leave. And so that, to make a long story short, that's the explanation there. I will mention more of that this afternoon. Any other questions?
What you have presented is really a configurational argument.
Right. The first part that we presented here is, it's not totally based on the statistical mechanics of the filling, because there was that power of Ken factor that involved the s to the minus 1/12, and that does come from the model associated with the zero-point field reduction. That's where that comes from. But essentially, you're right. I mean, we should have had slides here that separated those two effects. But the power Ken effect is a reasonably big effect. I mean, that did, when you get up to high S, that makes a big contribution there. But the point of it is that if the model, of course, isn't correct, then our arguments about H2 and T1 being the the whole show, of course, could easily be wrong. But I think evidence has shown that, in fact, the heat production is a surface effect, and the tritium production seems to be a surface effect too.
I'll make one observation, and that is that we now believe, as you say, the effect is in the surface, but it's also fairly clear that the effect is also only in small spots on that surface. So any measurement that has to use an average value, such as the average composition or the average surface, is not really looking at the nature of the nuclear active regions. And so how do you relate that which you can measure to that which you're trying to describe?
Well, I guess history would determine that pattern in a particular sample. In other words, if you had some cold fusion start out, you would end up with deuterons where there definitely was a boundary to the deuterons, and so you could have isolated pairs of deuterons to give the tritium production. That I guess would be my answer. That would be an historical thing for a particular sample, depending on its history. But again, at the metals and at the corners of metals and the surface of metal, the 0-point field would be reduced. And so that, in fact, is why you would expect this electron-catalyzed activity at these surfaces. You would find these blotches or spots of tritium at the surface.
Getting back to one of your previous comments, I don't know if it helps, but we have seen, and it's also been seen at MIT, charge emission from electrodes. So electrons do swim out of these electrodes.
That makes me feel very happy. Yeah.
Under some circumstances, I don't know what it means. I should also say you've done a much better job than I ever have of explaining my data.
Explain the what, I'm sorry?
Explaining my data, and you've done a better job
explain
of explaining it than I was ever able to do.
Oh, well, thank you very much. I might add that I once got a fax from Mike, and Mike is known in the cold fusion field, if I may say so without embarrassing him, as somebody who gives praise very grudgingly. And so here today, when you heard him give praise to Mel Miles, you have to multiply that by orders of magnitude to compare it with. So basically, it's like telling Mel that not only is he going to get a Nobel Prize, but by having activities like this, he may even get the Nobel Peace Prize. He may be the first physics winner and the Peace Prize winner. But basically, he sent me a fax which said, "Your model is beginning to be predictive." Now, ordinarily, if I'd gotten this from somebody, I would have said, "What do you mean, beginning to be?" But for him, it was like getting a Nobel Prize, frankly. I mean, he simply made that day.
I should send out more faxes. Like,
you said something about electron emission. How do you observe that? How do you measure that in a water solution?
no, gas loading experiments.
Pardon?
Gas loading experiments.
Yeah, yes.
How do you measure it?
As simply as with an electrometer, in fact.
I'm glad you answered that. I didn't know the answer.
But there are other ways, and it's a charged particle. But you can set up a polarity in a very high impedance circuit and just look at the current. It goes, you'll see a noise, and then every now and then the thing will go up 3 orders of magnitude, and the current will bang around and come back down. And we're still talking femtoamps. But,
I put a stethoscope on my cell, a stethoscope, and you could hear it.
Right.
Yeah.
I've heard that too.
Acoustic emission is a very good technique to apply to
It
these
talks to you, boy, does it ever.
These people are giving a good preview for my phonon laser thing. The next thing I'm going to do is I'm going to combine the mechanism of the electron catalysis of the actual nuclear tunneling with the phonon laser mechanism. When you combine those two, you have the complete story. And I'm sure for people that thought that some of the earlier talks were shaky, they went, "My God, we're way out in the stratosphere now." So, and incidentally, I think we've got quite a task. I was watching one of the talks, and several people were kind of talking next to me. This was in the back of the room. And the name of this great Japanese cold fusion scientist, Arata, was mentioned. And one guy turned to the other and said, "Aren't they all Arata?"
I have to tell you a joke. I had these stethoscopes on and I was listening to it, and one of the chaps from JPL came in and opened the RV door and stepped in and looked at me, and he says, "Now I know why they call you doctor." And I'm not.
Any other questions? Oh,
I think with that, we should close this morning's session and thank all of the speakers. We resume on schedule, whatever the schedule is. 1:30 sharp.